Hello, this is Benjamin Mayinger, a student working in the Using Ocean-Going Robots to Observe Wave Conditions team, specifically the CS team, and today I'm going to be showing you guys the directional visualization framework, which has been assigned to me. So let's get into it. First, just some background. The visualization framework is a module within our system that takes directional wave spectra and produces graphical representations of those spectra. Directional wave spectra will produce a polar graph illustrating the period, energy density, and direction of any swells acting upon the glider. The script associated with this block can be called on the command line with the following syntax, and then there you go. So let's get into the properties. So first we'll talk about the input. So the input data is formatted as a directional spectrum with 3 key components. Each point in the data represents an energy density at a specific period and direction in relation to the glider. The input data is formatted as a CSV file, and it is required for the program to validate input and handle bad input by producing a relevant error message. Furthermore, data is a matrix of float values describing directional wave parameters. Columns define directional bins in 5-degree increments, while rows correlate to wave period from a max period of 0.025 Hz to a minimum period of 0.56 Hz. So, and then finally, the code control transfer values stored in CSV files and passed to the visualization framework module as a command line argument. So before we actually get into anything, let's just look at our data. So this is an example of good data. So it's a little hard to see here, but there are 72 columns, and why that's important is because 360 divided by 72 is 5, so each column represents a 5-degree bin of direction, and then the rows define the period, and then each value in anywhere in this file represents an energy density at that specific point. So I have some good data, and then I have some bad data. So here is data that's just obviously not the right kind of data. Here's data that looks like it's right, but it's actually delimited by the wrong thing, so it's not actually a CSV file, even though it is, but we're just going to use that as an example for bad data. So this is how we call our script, just Python polar.py, and so we got to validate bad input. So let's imagine the user doesn't do anything, doesn't give any data. So error, too few arguments are given, then it tells us how we should call it. So now let's say we have 2 CSV files, and then we pass them in, and now it says too many arguments are given. So those are those 2 cases. Now let's actually get into some bad data. So let's run the first bad input, badinput.csv, and it gives us an error saying provided data doesn't match the expected data format. And now let's do the second one, and again we get the same error. So I'm going to actually show how that works. So here's our script. Basically we're just checking the length of the arguments to see if they're calling the script correctly. Then we check if it's a CSV file. If it is a CSV file, we try to open it. If it doesn't exist, then it'll throw an error there. Actually, I should probably show that that's what happens when you do that. So let's do bad input 3, which does not exist. And yes, it doesn't exist. So yeah, so then we open it, and then we check the format and check basically the amount of columns, and if it's not 72, we throw an error there. And yeah, so let's go back to our properties here. So the first one, our good data is formatted like this. The input data, they are CSV files. We do handle bad input and throw out relevant error messages. The data is a matrix of float values, as you can see in those CSV files, and they are of 32-bit precision. And the way it's defined is accurate as well. And then finally, we are passing them in as command line arguments. So that basically handles our input. But now we need to actually, produce our visualization. So before we get into that, I just need to explain where this data actually comes from. So the CDIP is basically doing exactly what we're trying to do, and they very kindly allow you to view their data. So you can see this is their representation of a polar plot, and this is the data that they used to produce that. So now, yeah, let's actually give it some good data. Do this one. And so here you can see we have produced a plot. So now let's go back to our properties. The visualization framework produces a graphical representation of wave spectra as three-dimensional polar graphs. Polar plot must be labeled with polar directions and period in seconds. Graphical representations are sized to 500 by 500 pixels in a windowed frame. This visualization has to support up to 72 by 56 data point resolution. And graphs must be displayed to the screen once computed, illustrating an energy density heat map. So I want to quickly check this one off. So we do support that. If we look at our input data, there's 72 columns and 56 rows. Let's go back. Graphical representations are sized 500 by 500 pixels in a windowed frame, which is also true. And actually I kind of went above and beyond here because we can size it however we want, and it is windowed. And can close it. There's also some built-in functionality just based on this matplotlib library that I've been using, which is nice. Yeah, so let's get into, I'm going to actually compare our data just to show that it is actually represented accurately. So here we have a polar wave spectrum based on the example data 7, and that's pulled directly from this website. And I actually have the, let's see, where is it? I have their representation of this right here. So you can see these actually are showing the same thing, although the way they show it is inverted because they have their high period going inwards and I have it going outwards. But if you look here, this swell is at about 8 seconds. And if you look here, that same swell is also at about 8 seconds. So this is an accurate representation of the data. And these, the radius labels are in seconds, and we have our directional directions, polar directions. So that's looking good. And now we're going to actually go into the code and just kind of run you through exactly what's going on here. So went over the input and how it's validated. We define our array, our data array, and then we just read in our data into that data array, and then we pass that data into this function, which is my plotting function. And so I'm using matplotlib, and specifically their contour f, which basically creates a heat map. It's a very nice function. But to set it up, I have to first calculate the bounding variables for labeling the radius. So this is basically calculating what the actual what these numbers are. Then I have to define my coordinate system here, and then we pass that into the mesh grid function, which basically creates two 2D matrices, which is what this function requires. We set our plot type, we set our title, we set our directional labels, we set our radius labels, and again that's using these variables to create them, and we have to convert hertz to seconds, so that's the 1 divided by here. Then we set certain labels to white and the external labels to black, so you can see here this one's black and these are white, just so it's nice and readable. Then we define our CMap, and basically CMap is a color map. I'm using Inferno, that's what this kind of color spectrum is, and then we pass our variables into contour F, and then 100 right here actually defines like how many levels are represented by those colors. So the higher this value, the nicer this looks. So I can actually show what it looks like when it's a bad value. It's pretty finicky to get this all working. This is, of course not very nice. You lose a lot of information here. But then, with the higher value you get a nice evenly spread spectrum that is accurate. And these are actually just like past iterations. You can see it as I was working through this block. So yeah, so let's go back to properties. So these are all met as well. We produce the visualization. It's sized correctly, it's labeled correctly, it supports our resolution of data, and it's displayed to the screen. So that's basically it. I want to thank you for watching my block checkoff. I hope you found it interesting. Thank you.